Alright, so here's our problem. We have our book. We're going to push on the book. It's 3 kilograms. We're going to accelerate it. So simple problem. We're just moving our book across the table like this. Alright, let's do our FBD. Free body. So you guys should be able to do this. So what are the forces acting on our book? Gravity. Fg. There's another name for gravity. What else could we call it?
Weight.
The weight. Yeah. So they're the same thing. Anything else? The normal force. This is the table. Pushing back up. The pushing force, right? So however you're pushing, sometimes we just call this like an applied force. You could also call it a push force is fine, or depending if you're using a rope, maybe it's a tension. And then anything else? Friction. So there we go. There's our free body. Okay, letter B. Alright, we're going to set up our equations, and again, this is kind of the big thing for today, is understanding how to do this. So I'm going to write it like this. We're going to sum up our forces. Now, just like last unit, we are going to treat x's and y's separately. So we're going to actually establish two equations. One is going to be the summation of all the x forces. One is going to be a summation of all the vertical forces. So we're going to kind of treat them separate. And if you have your picture, if you've drawn your picture correctly, this should be a very easy thing to do. So for example, in the x direction, all you're going to do is look at your picture and just add and subtract all the horizontal forces. So how many horizontal forces do we have here? 2. So you're going to say the summation is going to be F applied minus force of friction. And that's it. There's just 2. There's 2 horizontal forces. Okay? Now if you remember, Newton's law says what happens when you add up all these forces? What are they all going to equal? Not necessarily 0. Mass times acceleration, right? Remember, this is a net force. So your net force should equal mass times acceleration. I'm going to clarify the A here. This is a horizontal acceleration. Just like we did last unit, we are going to keep these separate from each other. Okay? Why don't you guys see if you can do the y equation? So we have the normal going up, we have gravity going down, we do subtract those two, and then we're going to set it equal to ma. We're going to clarify that this is ay. So this is the setup for the two equations, and in general you should get used to doing this. It's probably a little bit overkill on this problem because this problem's not that hard, but again, if you can get this on the easy ones, as we get to the more harder ones, it'll be you'll find those easier. Let's go ahead and start solving for things. Letter C should be no problem. How do we find the weight? 29.4? Okay, good. Alright, let's do the normal force. So to do normal force, we're going to now start using our equations here. So the first one is, normal force is right here. We're going to use this to find the normal force. Fg we just found, that was 29.4. The mass was given to be 3. So now the big question is, what is A? More specifically, what is AY? Vertical A. I did give you an A in the problem, right? What was the A that I gave you? 2. I gave you 2 way back here, right? Is that AY? That's AX. Yeah, so let's visualize the book sliding across the table. We're sliding our book like this, right? We're accelerating it like this. Vertical A would be this way. So as you watch the book go across the table, what is the acceleration in the vertical direction? 0. Okay, does everyone see that? Why is it 0? It's not going up and it's not going down. There's no vertical motion whatsoever. It's all horizontal. And so there is no actual vertical acceleration. So A is going to be 0 here. AY is going to be 0. All the motion is horizontal. If there was a vertical A, then it would be jumping off the table or going through the table, but none of that's happening. So notice what's our normal force going to be? It's going to be the same as the weight. Notice, if my book's standing still, the normal force is the same as the weight. If my book's moving horizontally, the normal force is still the same as the weight. If the normal force was greater than the weight, what would be happening to the book? It would be going up, right? That would mean the table's pushing the book up more than gravity's pulling it down. And if the weight was greater than the normal force, what would be happening to the book? It would be going through the table, right? Gravity would be overcoming the table's upward force. Alright, so that's easy enough. Normal force is therefore equal to it. Okay, let's keep going. Where are we at? Letter E? Friction. So you will always have 2 choices for friction, 2 equations. You have the equation that I just told you before. Friction equals mu times Fn. That's kind of the definitional equation. And then you're going to have the equation that you derived. So based on the summation of the forces, that also has a friction here. So it's kind of up to you to decide which one you're able to use in which situation. Sometimes you do this, sometimes you do this. I would recommend trying this one first because it's nice and easy, okay? You have to have normal force, which we just found. And you have to know mu. Were you given mu in the problem? No. So you actually can't use this one in this particular problem. So we're going to have to use this. Let's see if we can use this one. Were you given the applied force? Were you given the mass? And were you given the acceleration? Yeah. So you have everything that you need to find friction here. So let's do that. The applied force was 20. See if I can get. Guess not. Applied force was 20, and then we're looking for friction. The mass was 3. The acceleration was 2. So notice we have 20 newtons minus friction equals 3 times 2 is 6. Okay, easy enough, right? What's friction? 14 newtons. Make sure your answer makes conceptual sense. Does it make sense that friction is less than the applied force? Yeah. Friction, the applied force was greater than friction, right? Has to be. What would it mean if friction was greater than the applied force? That would be like I push this way, and what does the book do? Goes that way. Okay? Is that ever going to happen? No. So if I push this way and the book all of a sudden went that way, it doesn't make sense. So make sure your answers always make sense. Yeah.
So how are we sure which direction the force is going? And like when we say the force is going west, that we know because of like how we get that on.
Yeah, so sometimes they'll say it's east or west or something. If they don't, it just really depends how you draw it. I'll usually draw the motion to the right and then friction opposite to that. But yeah, you could do it the opposite direction and it would still work out. So are you asking me like for the answer? So friction would be what? East, west. And the applied force would be east in this problem.
So is force on the vector, so you don't have to put it, or?
It is a vector, but yeah, I mean you don't have to put it. Let's just say that. In here, you're kind of considering the vector nature of the force right here. So the fact that you're putting a negative on the friction here is it's considering the direction of the force. Okay, we're almost done. How do we find the coefficient? Well, once you know friction and you know the normal force, then we can find the coefficient using the definition of friction. So that's what we'll do. So we're going to say 14 newtons equals mu times 29.4 newtons. It's about half. How much? What are the units for mu? So look here, we have 14 newtons divided by 29.4 newtons. So what are the units? There are no units. Yeah, the newtons cancel. So this is what's called a unitless quantity. There are no units for the coefficient, 0.48.